Okay, so let's continue with Subir, who kindly accepted to give a talk to his own conference.
Well,
Thank you.
thank you. Well, as you know, it's Alessandro and William and others have been doing all the organizing, and but I'm happy to speak at their request. Thank you very much. All right, so I've changed my title a little bit, so to address this particular audience. So, certainly we know a great deal about CFTs in two space-time dimensions, and also via Bootstrap and RG, CFTs in three space-time dimensions. But there's a curious case of CFTs in one dimension that has, either thought to be trivial or meaningless. But in recent years, become clear that there is a new type of universality of CFTs in one dimension. And it's quite important for many things, in particular for it directly applies to various properties of charged black holes, as I'll try to explain. And some of these insights have also helped in recent progress in studies of strange metal, which I hope to say something about if there's time towards the end. Okay, so here's my ambitious outline. So what's enabled all this progress in the seemingly trivial case of one-dimensional CFTs is a solvable model called the SYK model. I should say, I probably have to minimize this here, maybe. Is that better? Yeah, okay. Yeah, so of course we did hear from Zohar and others about boundary or defect CFTs, where you have just one-dimensional CFT, but these are embedded in a bulk, which is also a CFT in higher dimensions. And that case is also quite well understood. But the SYK model and what I'm calling a one-dimensional CFT has some rather different properties, and that's what I want to emphasize. And it's those differences that will be important in remarks I'll make about charged black holes. And strange metals are not really CFTs, but we've learned a lot from these methods, and I'll hopefully say a little bit about that towards the end of my talk. Okay, so let's just begin with part one. What happened there? Yeah, okay. All right, so I'll talk about the SYK model and some of its properties. And one of the main lessons will be that actually it has some generic properties which are similar, although not identical, to CFTs in higher dimensions, but of the very heavy states, that are very large dimension operators, which Bootstrap so far has not said much about, for which we have very few solvable models. But these large dimension operators which describe black holes in higher dimensional CFTs, turn out to have a much simpler solvable realization in just one dimension. And so that's really what you gain by understanding this one-dimensional case thoroughly. All right, so here's the model. It's an extremely simple model. In fact, it made an appearance in nuclear physics in the 70s and 80s. There was a little bit of numerical study, but no understanding of its properties. So here I take a model of fermions with some, the Hamiltonian just has an interaction term between the fermions, a two-body interaction, U alpha, beta, gamma, delta, and alpha, beta, gamma, delta, just some indices of any label on these fermions that goes from 1 through n. So in this version, we're going to conserve the number of fermions. So there's a chemical potential and also a charge density Q that's going to be between 0 and 1. Okay, and really these three lines completely define the mathematical problem. There's no more to say, and you can go ahead and solve it. Everything follows from the properties listed here. So we'd love to solve this for a given set of U alpha, beta, gamma, delta. Unfortunately, that's impossible. But if you assume that the U alpha, beta, gamma, delta are uncorrelated random numbers, which we'll take to have root mean square value U, then you can solve it in the large n limit. But moreover, the solution is self-averaging. meaning that if you just picked a set of U alpha, beta, gamma, delta, you will get, for all practical purposes, essentially the same properties except for some very, very special observables that, are not very physical when you apply this to anything. Okay, so how do you solve it? Well, the simplest way to do it is just do a Feynman graph expansion and do the average term by term. And in the large N limit, the entire Feynman graph expansion can be reduced to these set of very simple equations. There's only a frequency dependence, the Green's function of the fermions, and sigma is just G cubed. And that's pretty much it. So these equations can be solved, and over the years we've been learning more and more about them. This is the set of equations we solved in 92, at least the leading scaling properties. And in some ways, you can say these are our bootstrap equations. There's a limit where I omega plus mu goes to 0 when the equations have a full conformal invariance, and we're just solving some set of self-consistency equations for the conformal structure. So in fact, if you go ahead and solve it, this is what you find. You can solve it in real frequency and finite temperature. Yes?
You have no space, no?
Okay, I'm just going to tell you right now. So if you solve the Green's function, for example, in time, in imaginary time, it has this form 1 over sine pi t tau, which is exactly the form you also see in boundary conformal field theories. And that is invariant under SL2R conformal transformations. So that's the conformal theory here. But this is the exact answer. Okay, and you can take a Fourier transform and get spectral functions at real frequency at finite temperature. And these have the very nice property that, the damping at finite temperature is just determined by the temperature itself and not the energy scale U. U only appears in the prefactor of this Green's function. Okay, so this is the full solution. Everything is known exactly. In the low frequency limit, frequency is much smaller than U. All right. Okay, so that's the easy part. And now it's looking, like a boundary CFT at this point. But then when you try to look at it more carefully, and try to compute, say, the partition function. So here's what I mean by the partition function. At fixed Q, you take the trace over all states, and that allows you to define the entropy. And also there's a density of states D of E, which is the sum over all the exact eigenstates. And this D of E is the inverse Laplace transform of the partition function. So one of the curious things is that D of E may not have a well-defined large N limit, because these energy E sub I, if you want to know every one of them, you have to know every U alpha, beta, gamma, delta. And they're, highly chaotic functions of them. There's no way to determine them. But even though that's not well defined, this Laplace transform does have a smooth large N limit, because you just convert every delta function to a decaying exponential, and then there's not much of a problem. And if you want to do the inverse Laplace transform, you of course won't get every delta function, but you'll get some coarse grain average of them, which in this case, I'll show you explicitly how that works. Okay, so one of the things we computed already this was around 2000. This is Antoine Georges and Olivier Parcollet. We just computed the free energy or the entropy. Now, as you know, a CFT in D dimensions, these spatial dimensions now, has an entropy that goes as T to the D. So here D is 0. So that should tell you the entropy should be just a number. And indeed, that's what it is. You get a number, S over N, as N goes to infinity, where N goes to infinity first, and then temperature goes to 0. You get a pure number, and this is what it is. At Q equals 1/2, we know it for all values of Q. Okay, so that's quite remarkable, and it seems to, this is somewhat analogous to the boundary entropy that Zohar mentioned, or the that Affleck and Ludwig did for the boundary CFTs. But here it's a little bit more serious because it's the entropy itself is n times S naught. So it's an extensive entropy. And it's in seeming contradiction with the third law of thermodynamics. But it's not really, and it is quite robust. But one of the things, if I took this temperature independent entropy at face value, and I then computed D of E by inverting these formulae. Suppose I put this in here and I do the inverse Laplace transform, then I get a very simple result that D of E is a delta function at zero energy with an exponentially large prefactor, which will turn out not to be correct, but yes.
Periodic now in D dimensions, I mean in D directions, so that.
Okay, so here I mean, you mean this here? This is a CFT in D infinite spatial dimensions. The entropy per unit volume is S to the temperature to the power D. That's a generic property, or if you made it finite in all dimensions, yeah, then it'll be L to the power D, or the free energy, this is just the Fisher-Dijen result. The free energy density is a constant divided by the volume, basically. This full volume. This is a completely standard result. This is simply saying that the stress energy tensor has dimension 2D or something like that. Yeah.
Why does now the temperature appear here as only?
So okay, here I'm taking you take a conformal field theory, which is infinite in space dimensions and periodic in the time direction with circumference 1 over temperature. Mm-hmm. Then the free energy density, or the entropy, which is a dimensionless quantity, entropy per unit volume in the spatial direction will be temperature to power D. This is a property of any CFT.
Okay.
Okay. Including the Wilson-Fisher fixed point as they first realized way back when. In fact, the coefficient is a universal number. Okay, so if I just take this Fisher-Dijen result and put D equals 0, I get a constant, and that is indeed the constant we computed. But in this zero-dimensional case, it seems to imply, if I just took the temperature-independent value here, it seems to imply that there's an exponentially large degeneracy in the ground state. And if this was the case, then you do have a violation of the third law of thermodynamics. But this is not the case, as I'm now going to show you. So we clearly have to look at corrections to scaling to get any temperature dependence at all. And so how do we do that? Well, in the spirit of this conference, if the simplest way to do this is in conformal perturbation theory. So we seem to have a CFT, so let's just do some conformal perturbation theory. So we take our scaling action SCFT. This is the original theory where you throw out the I omega terms. And then you perturb it with some infinite set of operators, O sub H. In fact, we know all the O sub H in this case. And then you do perturbation theories. Imagine these are scaling operators which have dimension H as a function. And so they decay in this way. And then you do just the usual conformal perturbation theory. And then you would conclude that the Green's function, which at 0th order was 1 over square root of tau, this is at 0 temperature now, would have corrections which have this power of H minus 1 here. And the entropy would also have subleading correction that vanish as temperature goes to 0, provided H is greater than 1, which it will always be. And so that this perturbation is an irrelevant perturbation. Okay, so we'd like to determine the spectrum of H, and you can do it with a bootstrap-like equation. What you do is you just look at the 3-point correlation function with the operator O at the red dot and 2 fermions. And in the large N limit, this is the entire set of, this is the full equation for this 3-point vertex. Then in the scaling limit, as in any CFT, the 0th order term vanishes. Is much smaller, so you can throw it out. And you get an eigenvalue equation for the vertex, where you have to solve for the eigenvalue E equals 1. So this is the exact bootstrap equation for the full spectrum of the operators. Then you make the usual assumption about the scaling form of the 3-point correlator. I won't go into it. You know the Green's function of the fermions, you know the G stars, and you just solve this equation. So in the end, you get any simple equation. This is the main equation right here for the values of H. This function has to equal 1. And that gives you the full spectrum of operators. Okay, so when you solve this equation, this is what you get. The smallest H is 2. It's the only one that's a rational number. It's just an integer. And this is, of course, the most important correction. And then there's some spectrum of dimensions of higher dimension operators that you can read off from solving this equation. So therefore, you conclude that the entropy, which was a constant to begin with, has a leading term that's linear in temperature coming from the H equals 2 operator. All right, so that's the leading correction from irrelevant operators. And all of this has been checked in great detail numerically. It works beautifully. I should mention Grisha Tarnopolsky has done a lot of very beautiful work in that direction. Yes? Yeah, so as we'll see, yeah, these are all the operators. They have dimensions of order 1. But what's heavy and what's not is a little bit more subtle, as we'll come to it. If you have the state operator correspondence in higher dimensional CFTs. Every dimension corresponds to a state on a circle or a sphere. Here, there's no space, so it's a little more complicated. So yeah, so there is no the state operator correspondence is not as clear, but I'll show you how it works. It's different. It's a bit different. All right, but let's just take this leading value, this S0 plus gamma T, and see what happens. Okay, so now we go back and we plug it in here into these formulae. S0 plus gamma T is the entropy, and D of E then gives you this result. This is actually very easy to determine. This is exactly the correspondence between the canonical and microcanonical ensemble. The left result is in the canonical ensemble. The right result is in the microcanonical ensemble. And this linear in temperature T corresponds to square root of 2n gamma E here. Here, E is the total energy, which is also of order n. So everything here is of order E to the n. All right, so that's and gamma itself is some number. It's not a universal number. It has to do with the leading irrelevant operator. It's some coefficient that you have to determine numerically. And for this particular model, you can get it quite accurately. All right, so let's compare this with numerics. So here's, you take a single set of alpha, beta, gamma, delta. This is 16 sites, but you can do more. And this is every eigenvalue binned in a certain way. So this is a plot of D of E. So if you want to know every eigenvalue, well, then it's hopeless. You need to know every U alpha, beta, gamma, delta. But if you're willing to course grain just a little bit, and I'll tell you how little, the properties don't depend on the U alpha, beta, gamma, delta. So in particular, when the energy is of order n, then you do indeed see, and it fits quite well, the density of states of this form that I just showed you. But what we are interested in, what happens when E becomes smaller. When E becomes not of order n, maybe it becomes of order 1, and maybe it becomes of order 1 over n, and maybe it becomes of order E to the minus n. We want to go all the way down. So if you look at the bottom, you see very explicitly that there is, in fact, no degeneracy at all. But the energy levels are still very densely spaced. And to be consistent, so if I take this formula and apply it indiscriminately by sending E to 0, then the density of states would be E to the n S naught. And so you would then conclude that the energy level spacing is E to the minus n S naught. So these are the states, if you wish, and they're even down to the ground state, they're exponentially close to each other. Now, if you look at CFTs in higher dimension, that doesn't happen. If you take CFT in 1 or 2 dimensions, initially the states are spaced by 1 over L, where L is the spatial size. But when you go above the black hole threshold, then they become very close to each other. So what's happening here is, and that's what simplifies life a great deal. You get black hole-like states all the way down to the ground state, and then you can compute a lot of things much more easily. Okay, yes. Yeah, 16, I think. I should say, to be completely honest, this is for the Majorana model, but not the complex model, but okay. It won't make much of a difference. The value of S naught is just half the value that I quoted for the Majorana model. Yeah. These were plots made by Grisha Tarnopolsky. I should have put that down. All right. Okay, so we want to now really understand this better. What is this really true? Numerically, that seems to be consistent, that the energy levels are actually exponentially small state. And this seems to hold, at least to some approximation, down to the ground state. Okay, so to do that, let's go back to this H equals 2 operator, which gave us this gamma T. And so we now have to really look at this H equals 2 operator at even lower temperatures. So the point is that I argued that this H equals 2 operator is an irrelevant operator. And that turns out that's correct, provided a temperature is bigger than U over N, where N is the system size. But if you want to go down to the ground state, you have to go to much lower temperatures, where the temperature is smaller than U over N, but of order exponentially small, e to the minus S naught. So this is where, in fact, this operator becomes much more important. It's not irrelevant anymore. It's very relevant in that direction. So it's what we call a dangerously irrelevant operator in some sense. But you have to go down to very low energies to see that effect. Now, naively, you might say 1 over N is the energy level spacing. And so what does this mean? But in fact, there's a huge space here for universal behavior, because the energy level spacing in a many body system is not 1 over N, it's e to the minus N. So there's still a very dense set of levels here, and there is some universal theory that you can write down. And that theory is, in fact, a theory of quantum gravity. Okay, so let me show you how that happens. So if you take the SYK model, you average the partition function, you do various Hubbard-Stranovic tricks, you can end up with this G sigma theory, as it's called. This is a path integral. This is an exact representation of the average partition function. G and sigma are functions of 2 times, and there's some action for G and sigma. If you take the saddle point in the large N limit, you get the same theories, the same equations that I wrote down earlier, which we obtained in a much more pedestrian way. Okay, so now we would like to take the saddle point and do the path integral. All right, so remember what I said, that in the conformal limit, this I omega term, this first term in the trace log, is irrelevant. So if you drop it. So if you drop this term, however, then you see that the remaining action has a huge symmetry, which was, okay. So then that symmetry is the following. So the action and the saddle point equations are invariant under time reparameterizations. So you go from time tau to time sigma, and you do the usual conformal transformations of the 2-point. These are bilocal fields. That's very important. And so you can, even at the level of Green's functions, do the conformal transformations. Only the saddle points are functions of the time differences, but the path integral is over bilocal fields. And there's also an emergent gauge symmetry, which is important to get the full partition function correctly, but I won't say much about it. All right, so this is a huge set of symmetries of the action when you ignore this UV term, the I omega term. So now what do we do? Well, we're going to have to do a path integral over fluctuations. And the proposal of Kitev and Maldacena and Yang was to go to the saddle point, but go only along the soft direction. So this is what you would do, like in a nonlinear sigma model. So here, I think you can think of this as some kind of co-adjoint orbit, if I've got those words right. So what you do, instead of doing the path integral over G and sigma, you do the path integral over this orbit. So G star is the saddle point, okay? And then you don't integrate over all G, you only integrate over a subset of G that you get by a rotation on the co-adjoint orbit of G star under this time parameterization. So f of tau is a monotonic map from a circle to a circle, diff S1 or something. And so that's the orbit that you're going to integrate over, because that's the soft direction where the energy changes only because of the presence of the I omega term. Okay. So you take that initial path integral over G and sigma with 2 times, and you convert it to a much simpler path integral over the time parameterization f of tau, and also the gauge transformation. And this particular path integral then can be done exactly, provided you know what the effective action is. So, I mean, the whole philosophy is quite similar to what Luca was doing for the Fermi liquid yesterday. You identify a set of soft directions, and then you just take your saddle point and move along the soft directions. And you try to guess using symmetries what is the structure of I effective. Now, one thing you will notice here is that is f of tau is a conformal transformation, is SL2R, then G equals G star. It doesn't move at all. So your path integral is therefore not over diff S1, it's over diff S1 slash SL2R. So this is what you get in the end. There's a path integral over df and d phi. You have to mod out by the infinite volume of SL2R. There's some effective action. And then from the symmetries and the requirement that the action vanish for SL2R transformations, this is its general structure, okay? So the point is here, the conformal group in 0 dimensions is the global conformal group is indeed SL2R, which is the same as SO2, 1. And diff S1, if you wish, is the local conformal group, which is broken by this Schwarzschild, this I effective, because there is some cost to integrating over time reparameterizations because of the I omega term. So that's the leading irrelevant operator that you have to keep. And then it turns out this gamma here is exactly the same as the coefficient of the entropy in the larger limit of the H equals 2 operator. So this is just a way of accounting for the H equals 2 operator to all orders. All right, so the amazing thing is this path integral can be done exactly. First shown by, sorry, that reference should be here, by Witten and Stanford. And then you can apply the results. So when you do that, this is what you get. So this was the result we had before, just from the large N theory and much more pedestrian type of calculations. And now you go to much lower energies and you account for the H equals 2 mode to all orders. And you ignore all the other operators. Then you get that this is the main correction, that the entropy, where's my pointer? Okay, yeah. So this was n times S naught plus gamma T before, and you get this minus 3/2 log of 1 over temperature. And if you really look at it very carefully, this is, you get this minus log n over 2 that was only worked out recently. And then you invert this to get a D of E. And there's also some subtlety in going from the canonical to the grand canonical ensemble. And then when you do that carefully, this is what you get. And you get the, this result here, exponential of ns naught times sinh of 2n gamma E. So what's going on here? Well, I should say this is obtained in various terms. This was something we obtained a long time ago. And this term, probably J. Kotler et al., the Stanford group was the first to write this down. And this we obtained just recently. Okay, so now going back to our numerics. So what I showed you earlier was that just from microcanonical argument, there's an e to the square root of 2n gamma e energy dependence. Now, at the bottom of the band, if this was some kind of random matrix, you expect a square root cusp. So we just put that in. And now you can see that the cinch answer that Kotler et al. Obtained is the simplest interpolation between the e to the square root of 2 gamma e and the square root edge. It has, it gets both of them right. And that turns out to be the full answer. So that's, that cinch square root of 2n gamma e is then the universal property, really, because this h equals 2 operator is present in every one-dimensional CFT. And it's a universal property, this set of density of states. Okay, so in fact, and numerically, this seems to hold down essentially to the ground state. Only when the temperature is exponentially small are you of order e to the minus n, are you sensitive to the individual levels. And if you're sensitive to the individual levels, well, then all hope is lost. You have to know your Hamiltonian. You can't, they're highly chaotic eigenstates of a many-body Hamiltonian. But if you're willing to coarse grain over some energy scale, which is, parametrically just a bit larger than e to the minus n, then you have a universal result. Also, this tells you that since, another important property of these states, you can see numerically that there's no simple relation between the first state and the second state and the third state. They're just totally different from each other in this huge Hilbert's Fock space. On the other hand, if you have a Fermi liquid or some system with quasi-particles, then the ground state and the first excited states are very simply related with each other, because you take a many-body state of n particles and you just move a few of them around to get the first quasi-particle state. So all the low energy states have very simple relation to each other. Here, that's not true at all. Every state is totally different from the next one. And that's, that's another way of saying the chaos. And that's what happens with black hole states. They're just chaotically random and exponentially dense. We believe similar thing happened in higher dimensional CFTs for the heavy states, but it's impossible to compute anything there in general. Yes? Correct. 3/2 log U over T. That came from the Schwarzschild path in Ergo. The cinch is just the inverse Laplace. This cinch square root of, so the 3/2 is extremely important in front of the log. When you take the inverse Laplace transform of minus 3/2 log T, you get the cinch square root of energy. That's where it comes from. If it was any other number, it's more complicated. I should say, so this is supposed to be, really like every CFT1 will have this cinch, but there's another class of CFT1s with supersymmetry. If you have supersymmetry, then the answers are a bit different, as I'll briefly mention later. But that's the only thing that really makes a difference. So it's either you have a Schwarzschild or a super Schwarzschild, and there's nothing else. I mean, the spectrum of the higher operators, this H equals 3.77, yeah, those can be different, but that doesn't affect the cinch. It'll affect things at higher energies of order 1, not at order 1 e to the minus n. All right, so that's a lot of work done on really a toy model, but this has led to some at least some understanding of the universal structure of CFT1s, which previously were thought to be trivial or wrong or inconsistent, but they're not, and they have this spectrum that you can see very easily in this particular model and also many other related models. Okay, so now let me talk about charged black holes. And there's a review article I've written that summarizes this from someone who's not an expert in black holes at all. So perhaps you'll enjoy reading it. All right, so let's go back to some history. Let's say we want to compute the partition function of quantum gravity, a very ambitious task for a black hole. For reasons that become clear, I'm going to talk about black holes that have a net charge Q. So you have some region of space where there's some charge Q and some mass M. We don't know anything about it, what it's made of, but it forms a black hole, and we're outside, and we're trying to compute the partition function of this black hole. And it turns out, so if you're outside the black hole, you're in vacuum, and the Q and the M is just a boundary condition in your equations. So you solve the equations in vacuum, and then that's how you get, say, the Schwarzschild solution when the charge is 0, or the Reisner-Nordstrom solution when the charge is finite. Okay, so what Gibbons and Hawking said, well, here's the impossibly complicated path integral that we should evaluate, but we're just going to evaluate it in the saddle point approximation. We're just going to take this theory and take its saddle point. And we're going to take the saddle point in Euclidean spacetime. Now, it so happens when you take the black hole metric in Euclidean spacetime, it has the shape of a cigar. What's going on? Okay, I'll just have to stand here and use this. So it has the space of a cigar, but it ends at the horizon of a black hole. And the time coordinate is a circle in Euclidean time, and the circumference is just h bar over temperature. And in fact, this is the only place h bar appears in this calculation, or if you wish, the definition of temperature in the circumference, the proper length of the time coordinate. Okay, so, and in fact, space-time just ends. So fortunately, you don't have to know anything about what's inside the black hole. You just go ahead and evaluate the partition function in this geometry. Take the saddle point, and there's some, very subtle, important subtleties about boundary conditions, which I will just not go into. But when you evaluate that, you get the famous answer of Hawking, which I'll write down here in the limit of 0 temperature for fixed Q. But at any temperature, the result is the following. It's the area of the horizon divided by 4, and then some fundamental constants. And if you take the limit as temperature goes to 0, in fact, for a charged black hole, the area remains finite, and that's the area I'll call A0. And then there's a term linear in temperature. And this is where I really need the fact it's a charged black hole, because you can't take the 0 temperature limit of a neutral black hole. Okay, so that's so far, it's just the Bekenstein-Hawking answer as evaluated by Gibbons and Hawking. And so that gives you this exponential factor. But we don't know what is the path integral around this. What are the corrections to this? Were not known until, in fact, very recently. Okay, but so this, this of course raises a lot of questions. If there's an entropy, then there must be some degrees of freedom, which are presumably inside the black hole. And without knowing anything about them, you've got an answer. And doesn't seem to depend on what's inside the black hole. Indeed, that's correct. And this is what in condensed matter would say, this is a universal property of a black hole. It's independent of exactly what the black hole is made up of. Okay. So at this point, I just want you to note some large number here, which is about n, plus 1 plus gamma t, constant plus linear in t, is exactly what you get for the SYK model. And there are many other similarities of Green's functions, which I noted way back in 2010. But of course, I didn't at that time know anything about Schwarzschians and these very singular corrections at low temperatures. But those, it turns out, also connect up very beautifully. So what's special about charged black holes? What's special is that if you look at the space-time metric on the outside of a black hole, very close to the horizon, it factorizes. It factorizes into ADS2 cross S2. Okay, and of course, ADS2, very familiar to you in conformal field theories. It's related to CFT1s, and its isometric group is SL2R. So very generically, there's a theory of quantum gravity here involving SL2R. But we can't just take the purely conformal limit to understand the thermodynamics, as we saw for the SYK model. We have to include a leading irrelevant operator. And that's exactly what you have to do here too. There's a boundary graviton, which is the boundary of the region where the space-time goes from 2 to 4, that's the action for this boundary graviton, in fact, as shown by Mardasena and Yang and Stanford, is indeed exactly the Schwartzian. So here's what happens. You start with Einstein-Maxwell theory in 3+1 dimensions. You do a dimensional reduction to this 2-dimensional space-time. You pull out the Bekenstein-Hawking answer, and you get a theory of gravity. This is in 1+1 dimension with a boundary graviton. And that's what's called JT gravity. And then you look at this JT gravity theory, and you apply the same kind of technology that I discussed for the SYK model. And what you find is that this JT gravity theory is, in fact, given by exactly the pattern-equal I wrote down. It has a time parameterization, f of tau, and it also has a phase rotation having to do with the gauge field. So we've already evaluated this path integral. The leading answer from the saddle point was here. I've told you this. That's the Bekenstein-Hawking Gibbons answer. And now we can just lift the results from the SYK model. And so therefore you conclude there's a -3 half log T correction also to the entropy of any charged black hole as temperature goes to 0. So here 1 over G is like N. So this is a term of order N, and this is a term of order 1. Now there's also terms which involve the log of the area. This is analogous to the log N terms in the SYK model. To evaluate those is much more subtle and requires you to know something about what's inside the black hole. Not everything, you need to know a few things. And that was also true for the SYK model. So in this case, these terms were initially considered by Sen, but he didn't know about the Schwartzian, so he missed a few points. And there's a very beautiful paper just a few weeks ago by Luca Eliasiu, Samir Mutri, and Joaquin Turachi, which got this strange looking number, -559 over 180 times the log of the area. So this number depends on the fact, it makes the assumption that the only massless fields in this theory of your black hole are the photon and the graviton and nothing else. If there were some other massless fermions or dark matter or something, then you could put them in, the number would change. But that's all it cares about. It's still a low energy property, but needs to know something about your low energy theory. Okay. All right, so now we have these results, and now we can take the inverse Laplace transform, just like we did for the SYK model. And so now you have an explicit expression for the D of E of a charged black hole at low energies. And it's exactly the same form of the SYK model. This is the Bekenstein-Hawking term. This is the Cinch correction of Kotler et al. In this case, the coefficient exactly. And this is the prefactor recently computed by Luca Eliasiu et al. So this is what the D of E looks like. And again, the important point is that there is no degeneracy. So even though an extremal black hole has a 0 temperature entropy, there is no degeneracy generically. It's some set of states. And now if I wanted to know every one of these levels, of course, I need to know what's inside the black hole. Is the string theory or what? I will need to know every last detail to get every one of those states. But if I'm just interested in some slightly coarse-grained value, it doesn't depend on them. And this is really the generic universal correction to any charged black hole without supersymmetry of the density of states. Yes. The prefactor is more than JT gravity, the -559 over 180. No, the JT gravity, if you wish, is a general theory of these diff S. It's a coadjoint orbit of diff S1/SL2R. That's the Schwartzian theory, and that's a universal sector in any CFD1 or any theory with ADS2. That's okay. That's a supersymmetry I'm coming to. This is the non-supersymmetric case, but right. So roughly speaking, I'll come to that. This is the very universal Hawking answer. There's many ways to get it. This is also as universal. This comes from the short and this prefactor, it depends on more details. You need to know it's beyond JT gravity. Yes.
And just on the slide before, you can't take the limit t to 0, no? Can you comment on this?
Well, t, again, just look at this picture. If your t is about e to the minus n, which is this level spacing here, then this doesn't work. So if you're sensitive to the individual levels, which requires to be at a ridiculously low temperature, then yes, you can't do it. But if you're just a little bit above that, I don't think we did a good understanding of exactly how much over. You can certainly be below 1 over n. You can certainly be, where, the question of the argument of the cinch. When the argument of the cinch is about a 1, it's certainly okay. So this is, some scale determined by the area and the Planck units. So it's still a pretty small energy. It's still okay. The question is when the argument of the cinch becomes exponentially small, then it breaks down. Yeah. Correct. Yes. Well, that's exactly the question I was addressing. If you average the partition function, it seems to be extremely good. Now, there are, of course, there's been a huge set of developments recently in people computing spectral form factors. That requires you to average 2 partition functions, and then they're connected by a wormhole. So then the wormhole corrections can become important in real time in the spectral form factor. And those, those wormhole corrections are measuring certain features of the level repulsion of these states. But for the density of states, this is all you need to do. Yeah, well, I mean, what observable you have in mind? I mean, if you're looking at the average energy, the entropy, the Green's function, they all self-average, for example. So, for example, if I take n sites, let's talk about the SYK model, which I know better. I take n sites, and you just compute the Green's function at every site for a given realization of couplings. They'll all be the same. What are the fluctuations in that? It's about 1 over n cubed. Yeah, so that's something. It hasn't been fully worked out, but yeah, so there are interesting, any kind of leading local correlator in the large n limit has no fluctuations. The question is what's the variance? And some of them, some observables like the Green's function have variance which is about inverse powers of n. For the density of states, I think also there are corrections of inverse powers of n, but much of those corrections for the average density of states can be absorbed into renormalization of this constant here. The cinch form doesn't change. So all of the corrections of the higher operators can be absorbed into redefinition of this effective coupling gamma. Yes, I think that's, well, the gamma is a number that you have to determine numerically. But then if you look at, well, we're just computing the average partition function. Yeah. When the question I think you were asking is if you take two different, you take the average partition function, coarse grain over some energy scale, and then ask what are its fluctuations. I suspect it's suppressed by some powers of n, but yeah. There's some results on this by Weber-Schardt, yeah, but I haven't studied that carefully. But what is certainly true in the large n limit, the leading term is self-averaging. Exactly what the corrections are a little subtle. And where the corrections are most important is when you go to the spectral form factors, and you have to include these exponentially small, what are seemingly exponentially small in the Euclidean version, but become very large in real time and give you these spectral form factors. And also the whole correction to the entanglement entropy and the page curve, that requires you to go beyond this simple geometry. Yeah. Yeah. Seems to be okay. You should really ask Luca et al. But yes, it seems to be negative in both the SYK model and over here too. Yeah. But it's just a small prefactor, power of A compared to everything else which is in the exponent. No, so what we're saying here is you have some UV complete of quantum gravity. I don't care what it is. At low energies, all I need to know is what are the massless field at low energies. So if you tell me your theory has 1 photon and 1 graviton low energies, and everything else is massive in the actual vacuum, in the phase you're in, then this number is correct. It's independent of the UV structure. It only depends on the massless fields at low energy. Sorry? Up to the prefactor, yes. Yeah. Well, okay, fine. What did I say? Well, I said Bekenstein. Yeah, but even that had not been done before. I mean, even the meaning of the Schwarzschild was not clear. So now I can, there were a lot of people questioning whether you could get this result from a Hamiltonian with discrete energy levels, and you can. Now, you might say string theory gives you the result, but string theory has a very different answer. String theory does have a degeneracy. So all of the calculations in string theory involve supersymmetry. And if you do the super Schwarzschild calculation, which was done recently by these people here, then this is what you get. So the original Straumann-Jawaffa calculation was of BPS states, which are highly degenerate. So they computed this prefactor of a delta function. Now, what's different is that a string theory has low energy supersymmetry. As long as you have low energy supersymmetry, the answer is different. Beyond that, then this whole SID structure is much more generic, which is in the SYK model. Yes, the power here is not in the SYK model. The 559 over 180 is not. Everything else is. Okay. Yes. I don't think you'd want to do that. Yeah, I mean, in the end, you go to this action and you add some more massless fields. Yeah, and when you do this dimensional reduction, you get this part, and you add in some other massless fields. This is the calculation that has been beautifully done by Iliescu and Tarachi and Heidemann and others. Yeah, so the phase part is related to gauge field, so you get both of these in SYK. In fact, the 1 over n factor there, yeah, that actually depends on certain detailed properties of SYK, which we test by other methods. So perhaps they know something about, all other operators with higher dimension. Yeah. All right, but I think it's fair to say the fact that this Bekenstein-Hawking entropy in charged black holes, which is every calculation in string theory is for charged black holes, is not a degeneracy, and that was not understood until very recently. And what's much more crucial is the fact that you have all these chaotic states which are exponentially close to each other. Which is also what happens for CFTs when you go to very large dimension operators in higher dimensions, like super Yang Mills, and people are thinking about those things now. Or even in CFT2s and ADS3, yeah, there's a lot of beautiful papers connecting the heavy operators to bootstrap and so on, but they're all There, the difference there is they don't have a actual CFT. They're always actually eventually working with bootstrap equations or with gravity. There is no Hamiltonian, which will give you every single level. Here there is, it's a random Hamiltonian, but it's there. You don't have that for CFT2s and ADS3, as far as I know. All right, great. 12:30, all right. Yes, so, I'm not a black hole person, but okay. So like a lot of this I've learned from especially talking to Steve Schenker, Juan Maldacena, and also Joaquin Toriachi. They've been very okay, all right. So yeah, so this I mentioned already. So what's the use of all of this? Well, once you have a confidence that all of this makes sense, then you can, even contribute very small corrections for the, which become very important when you're computing entanglement entropy, and that's been behind the whole series of exciting developments in the last few years, starting with this amazing paper of Saad, Schenker, and Stanford. Okay, so how much time do I have? So now I can come to a regime where I'm a little more comfortable, which was the original motivation for studying the SYK model, is to say something about strange metals. So I'll be very quick, 5 minutes. Okay. All right, so a strange metal is I think Luca mentioned this yesterday. It's a phase found in many correlated electron materials, most especially in cuprates. And over many decades of measurements, I think it's fair to say that people have now understood, or at least experimentally shown, that they kind of have a universal set of properties, independent of which material you're looking at. You could be looking at cuprates, twisted bilayer graphene, pnictides, certain heavy fermions. They all seem to share these 4 basic properties. And what I'm excited about is a recent theory which captures all 4 of them. So the most famous property is the linear T resistivity, but it's very important that the resistivity is small and in 2 dimensions, much smaller than h/e squared. T log T specific heat, so there's no sign of any zero temperature entropy, like the SYK model. So really have to go beyond the SYK model. The strange thing is the SYK model is a much better description of charged black holes than it is of real strange metals. Okay, but you have to, we've learned a lot, and the idea is to now put that knowledge to good use and make it more physical. The optical conductivity also has some 1/omega dependence with some logs. I won't go into any of the details. And if you look at the electron spectral function, it also has this marginal Fermi liquid form with the imaginary powered self energy going as omega. All right, so is there a system that can give you these properties? So one starting point for many, many theories, is set of fermions coupled to a boson. And Luca mentioned this yesterday. So I should, before I go any further, I should mention that all of this work was done with Avishkar Patel, who's a postdoc at Flatiron, my current student, How You Go, and a current postdoc, Ilya. And there was also earlier direction by Avishkar and Ehud Altman and others at Berkeley. All right, so the relevant model here, which generalizes to the physical model, is what some people are now calling the Yukawa SYK model. And this has appeared in various contexts in both string theory and particle physics and also in the condensed matter literature. So instead of having just fermions with a random interaction, you take fermions and bosons, usually with some trivial dispersion, and then you have a random Yukawa coupling. So this model, it turns out, in the larger limit, has basically the same properties as the SYK model. The value of the number S0 will be different, and these scaling dimensions H will be different. But the H equals 2 term, H equals 2 operator, the Schwarzschian all of that is exactly the same. So this is the model we want to study. So the way you study this is by writing down a G sigma theory and looking at its saddle point. So let me skip all of that. But let's go to something physical. So now, in real life, fermions are not just on one site. They're moving around and they form a Fermi surface. So let's imagine these fermions are undergoing a phase transition as you crank up some coupling J. And because of the phase transition, the Fermi surface elongates either along the Y direction or along the X direction. So there's a critical point here where these shape fluctuations become massless or critical. And in fact, Luca wrote down a positive, an action for those fluctuations right at the critical point. So a big effort over the last 20 years has been to understand this critical point and what are its physical properties. And it's only really been understood well in the last few years. But you can apply very much SYK-like methods to understand this theory. So at finite temperature, then there'll be a quantum critical region. And so one of the questions would be, is there a region here with the properties I listed? The short answer is no. So what happens? So if I just quickly summarize, you take this theory, you have some interaction J between the fermions, you decouple the J with the Hubbard Slatteramich field, and then you have something looking like the Yukawa SYK model, other than the fact that there's a spatial structure and there's no random couplings. Anyway, you can introduce a fictitious flavor space and take the large N limit, and this turns out to be a way to systematically study this. And you get a result with this omega to the 2/3 self-energy, which goes back to Patrick Lee, which is probably correct. There's numerical evidence for it too, and even for finite N. And Luca also mentioned this yesterday. Okay, but then if you try to compute the conductivity, you run into an immediate contradiction with observations. You find that there's a delta function at 0 frequency, just coming from translational invariance and the fact that the current and the momentum are not orthogonal operators. In fact, this is a problem with many of the black hole models of strange metals that were written down. They all have this delta function, at least in the early years, which was ignored, but more recently people have been going beyond it. But there's another serious problem. If you look at the optical conductivity at finite frequency, there were many papers saying there was a singular omega to the minus 2/3 term, and that has vanishing coefficient quite generally, shown by how you go in particular. All right, so this doesn't look like the real world. So if you have no disorder at all, it has this omega to the 2/3 self-energy, but it's not a strange metal. So we said, well, let's put in some disorder to break momentum conservation. So the usual way of doing that is to add a random potential. So in blue, I'm adding something that's not fluctuating. So the reds are fields, and the blue is not a field. It's just a given set of couplings, or in this case, a potential with some root mean square fluctuation with a delta function here. It's uncorrelated at different points in space. Okay, so you compute this, you get kind of half the answer. You find that there is a marginal Fermi liquid self-energy and a T log T specific heat. This is in fact known also a while back. But when you do the transport correctly and carefully, you find that there is no linear T resistivity here either, just a residual resistivity. So finally, you put in another source of disorder, and this turns out to be the key. You put in disorder not in the potential, but in the coupling. And from the Yukawa SYK point of view, that's the obvious thing to do. So the coupling, however, now it's convenient to rescale this to put the disorder, rescale phi, so that the disorder is here. And now we have the final theory. So it's very much like the Yukawa SYK model, but there is a uniform coupling and a spatially random coupling. The prime doesn't mean anything, it's just another symbol, and also a spatially random potential. If you now solve this in the SYK-like procedure, you can write down some G sigma theory. the new difference is that the G sigma theory has certain terms that are delta function in position. These are the spatial randomness, and other terms that are not. And you really have to take them all together and solve this pattern, this action self-consistently, and then compute response functions. So that's easier said than done, of course, but thanks to my 3 very able collaborators, we think we understand all of that now. And when the dust settles, basically, you get everything that's seen. At least the 4 properties I listed all come out correctly. And the key to all of that is indeed this spatial randomness in the Yukawa coupling, what we think is the most important thing driving all this ubiquitous strange metal behavior. All right, so let me conclude. So the SYK model is a toy model, originally written down just to find any model that didn't have particle-like excitations. And now we know that, it has chaotic behavior with these exponentially dense levels, and still the dynamics is of universal given by just h bar over kt is the only natural timescale at low energies, just like a black hole. And amazingly, this toy model actually captures certain aspects of the low energy theory, which is universal and more correctly than any previous model of a generic charged black hole. And so at least it gives you very explicitly a very simple Hamiltonian with discrete energy levels, which has all of the properties that you obtain from this Euclidean time path integral outside the black hole. You can reproduce all of that by a Hamiltonian, which I'm not saying that this Hamiltonian describes the inside of a black hole. It's a quantum simulation of the inside of a black hole in the modern use of that term. And then there are these extended models, which I very quickly mentioned, that we are quite excited about because they seem to be phenomenologically anyway so far, at least qualitatively capturing many of the essential properties of strange metals. So thank you.
Thanks. Any other question? Yes.
Could you set things up to describe holes with angular momentum? Kerr solution.
Yes, there's work by Sandeep Trivedi and collaborators at TIFR who've been doing that. I think there are some small differences, but I believe it can be done. Yeah, it hasn't been done to completeness the way the charged black hole has been done. There are people working on it. Yeah.
So there is the story of coupling 1D quantum system to reservoirs to let things evaporate, etc. And oftentimes what we use is a conformal boundary condition for the reservoir CFT.
Yeah.
Do you know if you really try to couple SYK to a 2D CFT, what can you get? What kind of boundary conditions do you get for the 2D CFT? Because conformal boundary conditions doesn't look quite realistic.
Yeah, I don't know. I mean, in fact, there's been work on that direction by, I think, Shinsei Ryu had a paper. There's also Pengfei Zhang and others who've been doing such things. In fact, a lot of these problems of evaporating black holes were studying systems like that. Yeah. So, yeah, I don't know if there's anything universal. I mean, it's very different from the problem of just a defect boundary. It's quite different from that because the SYK has its own dynamics, which is as important as the thing it's coupled to.
But for instance, both have H equal to operators, I guess, right? Also in a defect there is.
Yeah. So I must profess ignorance, but there have been a lot of papers on this. Yeah. And I think the most recent was just on the archive last week by Shinsei Ryu and others. I've been meaning to read that. It's sitting on my desk. They take the bulk system and they integrate it out, and you get a Lindbladian theory of SYK, and then they work with that. Because you still think of the bulk as as a bigger infinity than the boundary. Yeah.
So you said when you have supersymmetry, the density of states is very different.
Yes.
Is it
yeah.
because you have additional states?
Well,
In the,
so it's no, I don't know if it's additional states. The question really is, and this was a puzzle that Preskill and Wilczek had talked about earlier before the structure was understood. So the question is really, whether so everything here is shown in this picture has an exponential prefactor. This prefactor is in front of everything. So now the only question is there a gap and is there a delta function? Or there is no delta function. So it's just a rearrangement of the low energy density of states. So what happens in a supersymmetric black hole, and really everything in string theory, where you can solve this, there are BPS states, which are all at zero energy in this normalization. And you just count them, and they have the same energy. And more recently from the super Schwartzian. So if you take the super Schwartzian path integral, that doesn't, there's a prefactor here that comes from the just the topological term in gravity. You don't know what it is, but the rest of it, the energy dependence and the temperature dependence, comes from doing the path integral. So if you do the path integral for a super Schwartzian and you take its inverse Laplace transform, which is what was done in these papers, you will get a delta function plus a continuum. So this whole shape, apart from the prefactor, comes from the inverse Laplace transform, the super Schwartzian path integral. So I think string theory only knew about this delta function. And I think it's fair to say people assume this delta function was always there. It's not. And the fact there's a gap of this magnitude, delta is about a 1 over the entropy. I think these people are the first to point it out. Also, although it's implicit in the paper of Witten and Stanford, they've done all of these cases there. They don't comment about implications for various things, but I'm sure they understood it.
Any other question? Okay, otherwise, let's thank Subir again.